Our second speaker, we've got Catherine Regan, who's a final year PhD student at MSSL. Catherine's studying dust and Mars's magnetosphere, and she's also heavily involved in outreach. So, for example, she's PI of the project Eyes on Mars, and she's also vice chair of both the MSSL Outreach Working Group and STFC's Public Engagement for Early Careers Forum. So, Catherine, if you'd like to share your screen, and I'll let you start your presentation.
Okay, can you all see that okay?
Yep.
Okay, fantastic. So thank you for the introduction. So yeah, I'm a final year PhD student. I'm at the Mars Space Science Laboratory. So I'm also part of the Centre for Planetary Sciences, which is everyone at UCL and Birkbeck that studies anything to do with planetary science as well. So those are my two affiliations. And I've got my list of co-authors there. I collaborate with lots of people, but in particular, I have a very close collaboration with the University of Leicester as well. So this work has also been heavily influenced by the Mars group there. So I'm going to talk about my PhD research. I'm going to try and summarize 3 years of work into a short presentation. So if I go too fast, if you want to ask something, if I don't go over it in enough detail, then please do just either get in contact with me or ask a question at the end, because I'm aware I'm going to try and cover quite a lot of content. So I'll start off with a bit of an introduction to Mars. It's my favorite planet. If you don't know much about its evolution, then you're in luck. I'm going to talk a bit about that now. So about 4 billion years ago, Mars was very different to how we see it today. So it had a global magnetic field. So it had a magnetosphere, very like what we do at Earth. And because of this, there was a very thick atmosphere full of carbon dioxide and water vapor, and there was water. So we had oceans in the northern hemisphere of Mars. We had river channels, and these created a lot of the geological features that we're familiar with on the surface today. But now there is no global magnetic field. What we have is an induced magnetosphere due to the interaction with the solar wind. And the loss of atmosphere from the planet has left a very dry landscape. So it's very dusty, very arid, doesn't look like a very habitable place. But what's really interesting is that when we look close at the rocks, and this was first done by Mars Global Surveyor, when we looked at the magnetic field, we actually saw remnant magnetism in the minerals, in the rocks, in the magnetic minerals. So this is one of the crustal magnetic field maps that was produced by Mars Global Surveyor, and there's been tons of maps done since. But there's this area in the southern hemisphere that particularly has a very strong signature of crustal magnetic field strength. And this can create mini magnetic fields, so mini magnetospheres here in the southern hemisphere. And this is a really interesting feature. This is a signature of the global field that was present 4 billion years ago. And this actually has an influence on the magnetic environment of Mars. So I'll introduce the magnetic environment, but what's worth noting is that these signatures can actually be seen out into the magnetosphere. So because there is no global magnetic field, there is no protection from the solar wind. So the solar wind can go very, very close to the surface of Mars. And when it gets there, it ionizes the atmosphere. This gives the system a lot more energy, and it strips away atmospheric particles into space. And this process induces a magnetic field. So we don't have an intrinsic one, we have an induced magnetic field due to this interaction of the solar wind with the planetary obstacle, which in this case is Mars. Venus also has a magnetic environment like this, and Titan and also comets, their magnetosphere is quite similar to Mars. So a bit more detail into the magnetosphere itself. So we have the solar wind that's going out into interplanetary space, and I've put the distance from the sun to Mars on the bottom there in kilometers. And the first boundary we encounter it's like Earth. It is the bow shock, but it's a lot closer to the surface. So it's about 8,000 kilometers away from the core of Mars. So this boundary is marked as the solar wind is deflected and slowed, and it begins to kind of divert around the obstacle. So the plasma here is heated, it's compressed, and when we look at data, this can be seen by an increase in the magnetic field magnitude. So there's a lot more variability in the magnetic field, and we see a big increase in the electron and ion flux and the density as well. So that's the signature of the bow shock. We then enter a region called the magnetosheath. So this is characterized by low magnetic field, magnetic field strength, and superthermal electrons. And this is a region of the slowed solar wind plasma. So that kind of makes up this region. And then the next boundary we encounter is called the induced magnetospheric boundary. This can sometimes also be referred to as the magnetic pilot boundary. It has different names. It's mainly because different instruments have been used to detect this boundary, but I'll be calling it the induced magnetospheric boundary, or IMB. And this can be seen in a big increase in the magnetic field strength. The electron temperature decreases, but there's an increase in the electron density. And then we enter the region of the induced magnetosphere. So this is where the planetary plasma population is really dominating. The magnetic field also piles up here. And this is where we have the planetary population, really. And then closer to the surface, there are a few more boundaries, including the mini magnetospheres that are in the southern hemisphere due to the crustal magnetic fields. We also have an ionopause marking the upper part of the ionosphere that isn't always present. So this environment is a bit more variable, hence I put it in dashed lines. But I'll mainly be focusing my research on the bow shock and the induced magnetospheric boundary. So global dust storms on Mars. These are really neat events, and they occur sometimes during dust season. So during the Mars year, we have a dust season, which is just like we have hurricane season here on Earth. And it happens when the southern hemisphere is in its summer, and that's where Mars is at perihelion, it's closest to the sun. So there's a lot more energy going into the system, which means that the dust can get uplifted. And every Mars year, we do have dust storms. But these are regional storms. But what we don't understand is why some Mars years, these regional storms can either grow or they can merge, and they produce a singular storm system that covers the entire surface. So these last occurred in 2018, 2007, 2001. Doesn't really seem to be an obvious trend as to why some Mars years they happen, some Mars years they don't. It's kind of an ongoing area of research for surface and atmospheric scientists. But the main thing is that the entire surface is one system. It's one singular storm system, and these can last several months. Visually, they're extremely impressive events. I mean, the picture on the left, you can see Olympus Mons and the Tharsis volcanoes. You can see the ice cap, and you can see all the different geological features. And then a month later, everything's covered in a dusty haze, and you can just about see the same features, but it's a lot more difficult. And the public really care about global dust storms because the last one in 2018 is what ended the Opportunity rover, because the dust storm covered the solar panels on Opportunity. So not only do we care about them from a science point of view, the public also seem to care about them as well, which is quite nice. So why do I care about them? I am looking at signatures of the two most recent global dust storms, the 2007 and the 2018 ones, and seeing if we can see signatures of this atmospheric event in the magnetosphere. So to do this, I am looking at how the bow shock and the IMB boundaries vary during these two events. And to do this, I'm using two missions. So the first mission I'm using is Mars Express. So this is Europe's first mission to Mars that just celebrated its 20-year anniversary. It's still going strong. A fantastic mission. And in particular, my analysis has been done using the Aspera instrument. So I've been looking at the electrons, ions, and heavy protons on Aspera. So I've been able to use Mars Express for both 2007 and 2018 because it's been there long enough. And then for the 2018 storm, I have the addition of MAVEN, which is a NASA mission that just celebrated its 10-year anniversary. So lots of Mars mission anniversaries this year. So I can only use this for the latter storm, but I've been able to use the ion and electron instruments, and the MAVEN also has the nice addition of a magnetometer, which is providing very useful, which unfortunately Mars Express doesn't have. So that's my instrumentation. My methodology, I'm going to go over very, very quickly. But basically what I did for both dust storms is I looked through all of the data by eye, because there are automatic detection models, but they're not 100% accurate. So the best way to do it is by eye, but I identified both boundaries from the electron, ion, proton data from the instruments. So this first dashed line is where we're going from the planetary plasma region, crossing the IMB into the magnetosheath, and then this second boundary is marking the bow shock. So I did this for months of data. I got thousands of crossings. I was seeing spectra in my sleep. It was a very long process. But once I got my catalogue of boundary crossings, I then applied a 2D boundary model. This is the only maths I'm going to include, don't worry. So I calculated this distance called the terminator distance, RTD, which is the distance from the center of Mars to the boundary, where the boundary is going from day to night side. So calculating this parameter basically meant I could compare all of my boundary crossings, because they all had different solid zenith angles. So they were occurring at different points in the Mars day, which was having quite a big influence. So doing this parameter meant I could remove the influence of the time of day on Mars and do some kind of nice comparisons of what's happening. So my results for 2007, this is this parameter, the terminator distance, RTD, for the induced magnetospheric boundary, so the boundary that is closest to the surface of the two. This has recently been submitted, and I'm going to try and summarize the whole paper with one or two slides. So I binned all of my data to look at how the terminator distance varies based on where you are over Mars geographically. So I wanted to kind of see if our position with respect to the surface had any influence on my results. And this was because this had been done with kind of over 20 years worth of data from Mars Global Surveyor and Mars Express. And the induced magnetospheric boundary was found to bulge over the crustal magnetic fields. So in the southern hemisphere, where we have this very strong band, the IMB bulged. So we had an increase in the terminator distance due to the occurrence of the crustal magnetic fields. And this was summed over years worth of data from multiple missions. And it's a kind of accepted fact in the community that the IMB bulges over crustal magnetic fields. Because that's what I expected to see. I'll just get rid of the map so you can see the plot. If you look across the -45° latitude band, my data goes from red to yellow to red. But with a bulge, you would expect it to go from yellow, red, yellow. So this is indicating that we're actually getting a bit of a depression over the crustal magnetic fields as opposed to a bulge, which is the opposite of what you would expect. So I wasn't completely convinced by this. So I did a lot of fact checking, a lot of code checking to make sure this was correct. And this is the signature. Due to the 2007 global dust storm, we're seeing a dip in the induced magnetospheric boundary. So to kind of try and explain why this could be occurring, I created this schematic. So my explanation for this is that where we've got these crustal magnetic fields, we have closed crustal field lines, closed magnetic field lines, sorry, due to the signatures. So globally on Mars, we're having an uplift of dust, we're having an uplift of aerosols and atmospheric particles. And we know that dust storms, research has been done into dust storms to show that we have an increase in the amount of atmosphere being lost due to a dust storm occurring. And this is because this uplift enables more reactions to take place and ionization for it all to be lost into space. So that's happening globally. Now, what I'm suggesting is that over the crustal fields in the southern hemisphere, we're still having this uplift of particles, but our charged particles are confined. So we don't have as many charged particles here to react with the uplift of the atmosphere and the dust and the aerosols. So although there's uplift, we're not having as many reactions take place. There's not as much ionization happening over the crustal magnetic fields compared to elsewhere. So this is why potentially we're seeing this dip in the induced magnetospheric boundary. So this was really exciting. I presented this to the community last month, and it's a novel result. No one seemed to think I was really wrong, so that's always positive. So I thought, okay, I've finished this storm for 2007. What I'll do now is I'll do the 2018 global dust storm and see if I get the same results. This is perfect. We've got 2 missions now. We've got loads and loads of data, so that's what I'll do. So this is ongoing. So this is one of the initial plots from this. So I've split the boundaries up. So I've got bow shock on the top panel, the IMB on the second panel. And I split my data up into 3 time periods. So time before the storm, during the global dust storm, and post global dust storm. And the post global dust storm here is defined as when the surface conditions return to normal. So the surface temperature and pressure has returned to normal based on data from Curiosity here. So the pre-storm data is in green, the storm is in maroon, and then the post-storm is in blue. So what we're seeing for the induced magnetospheric boundary and the bow shock is a big increase of a few thousand kilometers of the mean terminator distance due to the occurrence of the storm. So this is really nice. We're seeing a big shift. The boundaries are moving further away from the surface due to the occurrence of the dust storm, which is quite nice. That is kind of what I hypothesized would be happening. But what's really interesting here is that, particularly for the bow shock, when we're going towards the end of the global dust storm, so the post-storm phase, we're actually seeing a further increase of about 1,000 kilometers. So the boundary is actually moving out again. So although the surface conditions have returned to normal, this is indicating that the magnetosphere hasn't actually recovered, and we're still seeing an effect of this dust storm there. So this is really interesting. And I thought, okay, fantastic. Now I'll create another map and do some binning and compare it to the 2007 storm, so I can see if we're seeing a nice magnetic field signature. So I did that, and unfortunately, right where most of the crustal fields are, between 0 and -45-degree latitude, I've got a data gap, which is just the way science goes, isn't it? So that was really frustrating. So unfortunately, I can't get an initial result from this. I can't make any conclusions because we've got this gap. I can't compare really just from this plot areas of strong and weak crustal magnetic fields, which is really frustrating. But my plan now is to actually implement some crustal magnetic field models. Because we've got the addition of the magnetic field data from MAVEN, I can now do some nice magnetic modeling to hopefully see if we're seeing the same signature as we did for the 2007 storm. So the 2018 results are ongoing. It's what I'm working on at the moment. But I think I can say quite confidently that both boundaries seem to shift outwards due to the occurrence of the storm, which is really, really nice. But what I need to look at in more detail is the recovery time, how long it takes these boundaries to go back to their pre-storm conditions, particularly for the bow shock. It's a very interesting feature that it's still staying elevated outwards. And annoyingly, we've got a data gap over the crustal fields in the southern hemisphere for the IMB, but I can now implement some better boundary magnetic field models to my boundaries to see if I can deduce anything despite the data gap. So in conclusion, the results from 2007 and 2018, they show that each storm is different. I think just kind of like events here on Earth, we can't assume that one storm gives the same signature each time. They're going to have different kind of growth mechanisms and evolutions in their behaviors. So the effect on the magnetic environment is going to be different as well. But 2007 showed a really nice feature in the depression of the IMB over crustal magnetic fields. This hasn't been seen before. And 2018 may show that, it may not. Hopefully I'll be able to tell you that very soon. But what's really exciting is the next dust season on Mars, which is happening in summer 2024, is going to be happening at solar maximum. And since we've had missions there, we've never had these two coinciding at the same time. So, I mean, this may be the ingredients for a global dust storm. We don't know. If so, there'll be a lot of data which I can hopefully look at, which would be really, really exciting. But in the meantime, whilst I'm waiting for that, my further research is looking at the recovery time of the 2018 global dust storm. So this is the final project I'm going to be doing before I start writing my thesis. I think I may have gone a little bit over my time, but I hope you enjoyed, and I look forward to hearing all of your questions. Thank you.